Alright, so let's prove this fact about maximal ideals. So let I be an ideal in R. We want to prove it's maximal if and only if R mod I is a field. By the fundamental isomorphism theorem for rings, the map that sends an element R to R plus I is a bijection between subgroups of R which contain I and subgroups of R mod I. And this is because the map that sends R, the reason that the fundamental isomorphism theorem applies is that the map that sends R to R plus I is a ring homomorphism, and that follows from the fundamental theorem of ring homomorphisms. Okay, so next we know I contained in H contained in R is an ideal if and only if. So this is, we know H is an ideal, so that's the thing that we're talking about, but it just happens to be, it happens to contain I and be a subset of R. It's an ideal if and only if eta of H is an ideal. So suppose I is maximal. Wait a minute. Bijection between subgroups of R which contain I? Or subgroups? Should these be ideals here? Give me a second. I'm going to check this real quick. Fundamental theorem for homomorphisms. Wait, no. No, it's the first isomorphism theorem, which is this. Set of subgroups containing this. H is an ideal if and only if eta H is an ideal. Okay, so yeah, we have that bijective correspondence, but we also have that H is an ideal if and only if eta H is an ideal. So that's what we're using here. Let's see here, and let's just remember. Okay, so that applies so long as eta is an epimorphism of a ring R onto R prime with kernel K. The map that sends the map that sends R to R plus I is clearly an epimorphism, and its kernel is I. Because anything in I will just go to I. It'll go to R plus I, which becomes I. So what we really have is by the fundamental isomorphism theorem, yeah, that's the first. Oh, it's not the fundamental isomorphism theorem, it's the first isomorphism theorem for rings. The map is, I bet, I'm just going to erase this. The map which sends eta of R to R plus I is such that and the obviousness of eta being an epimorphism is from the fundamental theorem of ring homomorphisms. The map is, so by fundamental first isomorphism theorem, this map is such that for any okay, here we go, equals r plus I is such that I contained in H contained in R is an ideal if and only if, I don't know where that dot came from, if and only if H is an ideal. Okay, that's the only thing we need. I don't know why I include the other bit. I was probably just copying and pasting isomorphism theorem without really thinking about it, which is not something that you want to do in math. So suppose I is maximal. Then any such H is either I or R. So the ideals of R mod I are eta of I, which is just I, and this is a singleton set I, and so which is like the zero ideal, and eta of, because I is the zero element. Anyways, and eta of R, which is precisely R mod I. And we know that this that if you have a commutative ring whose only whose only ideals are these two, is a field. Yeah. Right. Well. Yeah. Yeah, we proved that. Thus, R mod I is a field. Because we have commutativity. Even if you didn't have commutativity, you would just have R mod I as the divisor ring. That was one of the other exercises, but we have commutativity, and so this is a field. Thus, R mod I is a field. And so the reverse direction is pretty much the same. Perhaps we could have done an if and only if thing, but I don't know. I didn't work out the details. So let's just do it. If R mod I is a field, then its only ideals are I and R mod I, and the only ideals H such that I contained in H contained in R, R, I, and R, so I is maximal. So was there something else I want to say? The only ideals are, yeah, and so we do use the fact that H is an ideal if and only if eta H is an ideal, because yeah, that verifies that not only when we take them forward and backwards under the map do we get ideals, but in particular this, we know that eta of I is I, and we know that eta of R is R mod I. And so we know that those are two particular, so we have two particular sets in R, or two particular ideals in R who get mapped to ideals under eta. But the fact that these are the only ones comes from the fact that this correspondence is bijective, because it's an if and only if. So there we go. This completes our proof.